A ladder of length L and mass M leans against a wall, making an angle of 29 degrees theta. That's kind of a shallow, it's okay, with the horizontal shown in the figure below. A horizontal cable with tension 250 newtons is anchored to the wall and attached to the center of the ladder. The bottom of the ladder rests on a frictionless surface. Frictionless, not a good way to rest a ladder. There is also no friction between the ladder and the wall. The system remains in equilibrium. Okay, so the whole thing is stationary, not moving. So what is the exponent of the force applied by the ladder to the wall? Okay, so first thing to do is you think of this in terms of the same thing as if we were just doing linear motion and thinking in terms of things linearly without respect to torque. So I'm going to write up the kinematic equations. So kinematic equations is acceleration. We're going to say that's constant. Velocity equals at plus v naught. And x equals 1/2 at squared plus v naught t plus x naught. And so what we're going to do here then is pretty much the same as what we would do with the kinematic equations, except now we're going to use angular velocity, acceleration, and rotation. So the conversion between the two is a equals angular acceleration times radius, v equals omega r, and x equals theta r. These aren't necessarily all that intuitive, but it makes sense from a dimensional analysis point of view. So if you look at, let's say, velocity here, we have omega, which is radians per second. We'll say it's radians per second, times r, which is measured in meters. Now radians, it's dimensionless. There is no dimension associated with radians. You would think that it would be meters or distance, but it's not. So a lot of times when I write this, I put a parentheses around radians to say that it's not actually a dimension. It's not really there. We could leave it off and be fine, but I like to put it in just to be clear. And so when you have angular velocity times radius, you get meters. That's supposed to be an m. I know there's an extra little hump. Don't worry about that guy. Times seconds, which gives you meters per second, which is velocity, which is the dimensions for velocity. Now, you could also look at it from the this portion right here, x equals omega r, and you can think of it like a circle. You have a circle, the distance around the circle is 2 pi r, and the radians around the circle is 2 pi, and then to get the distance, you then multiply by r. So 2 pi r. Kind of makes sense. Okay, so that's the conversion between linear and rotational units. Now, if we take our old kinematic equations and we plug these in, we have, let's see here, so we'd have alpha r. So this would basically be that alpha r would equal alpha r. So this would be omega r equals alpha r t plus omega naught r. And then for the bottom, we have, theta equals, theta r equals 1/2 alpha r t squared plus omega naught r t plus omega naught r. And you can see all of these have an r for every single variable. Well, except for t, I guess. But that's okay, we don't want it for t. So these cancel. I know I'm doing this across multiple equations. Not kosher at all. And basically, long story short, we're left with alpha equals alpha, omega equals omega t, no, alpha t. Alpha t plus omega naught. And we have theta equals 1/2 alpha t squared plus omega naught t plus your initial theta naught. Okay, so gone through that. Get rid of this little guy right here. Leave that up there for now. And basically what we do is we have the kinematic equations now for angular. And they're pretty much exactly the same. And so all this should kind of trigger in your mind that all the concepts are going to be the same. So when you see something like in equilibrium, not moving, stationary, what that should tell you is like, okay, so that means that acceleration equals 0, which means that velocity final equals 0 times time plus initial velocity, which means that the velocity will be 0, or velocity will be constant. And if we know that it's not moving, that everything is stationary, they say equilibrium. I'm going to assume that also means stationary in this case because it's a ladder against a wall. It's not going to be spinning or flying around. So we know that v equals 0, and they would also know that x final equals x initial because we have both v naught and acceleration, which are 0. So long story short, well, I guess we could have jumped out from this point. We know that the sum of all forces will equal 0 in every dimension, specifically the x and the y. We could say the z, but this is just two-dimensional at this point. And we know that the sum of all torques, which is the rotational equivalent of force, will also equal 0. For those of you who don't know, torque is defined as r cross f. So you have a radius, and you have a cross product between radius and the force, and that will give you the torque. So we have no linear motion, so all the forces will sum to 0. We have no torques, so all the we have no rotational motion, so all the angular torques will sum to 0. Okay, and so that's kind of like the jumping off thought process that you should have for this kind of problem. Okay, so let's redraw this picture real quick. So we have a ladder, looks kind of like this. Change colors, go to purple. We have a force going this direction called force tension. We have a force going this direction. I'm going to call it force gravity. It's gravity is acting on the whole length of the ladder, but we can basically sum it up and say that it's acting on the center of mass of the ladder. We also have ground here, and it's allowed to slide this direction. I'll probably get rid of that. The ladder's allowed to slide in this direction, and the ladder's allowed to slide in this direction. So those directions we can't have forces going on that direction because it would just slide. But we do have a force going up this way, a force normal, so the ladder's being pulled down. And we have a force going this direction, another normal force. I'll call this force normal x, force normal y, because it's x and y direction. And these are the four forces that are acting on the ladder. They'll create torques. And it kind of makes sense there'll be a torque. If you look at just the x and the y direction, so if you look at these 2 points here, you have them acting in opposite. You have two, I guess, forces that are parallel to each other but not like overlapping. And so they won't cancel each other out and it'll create a rotation. It kind of makes sense if you had like a stick like this, and you pull down on here, pull up on here. Here's be the center force. It makes sense that the stick would rotate in that direction. And that's basically what's going to happen here. So we're going to have these will create a torque going that way. I'll call this going clockwise. And this will create a torque going, which way is that? This way. I'll call this torque counterclockwise. There we go. That works. So this is the model that we're going to work with. So with this kind of thought process in mind, now I spent a while going through all of this. I wouldn't say you should, if you're practicing, sure, write this down. But like on a test, you're better off just trying to have this as a mental picture. You can maybe draw some forces on here, like do the free body diagram on the picture given to you, but you really don't have time to go through this kind of analysis as explicitly as I am. Okay, so the first question is, what is the x component of the force applied by the ladder to the wall? So I'm going to just say, I'm not going to worry about the magnitude here, because It's like, well, should it be to the left, should it be to the right, which one applies it on which? They're basically saying you have this string, what is it? Is it a rope? Attached. It's just attached. You have some sort of ligament between the wall and the ladder, and that's going to be the only thing providing an X component force applied by the ladder and the wall. You could also maybe say, so there's like a ladder to wall, and then there's a wall to ladder. So there's two forces between the wall and the ladder. This one, which is the one I think they're talking about here, by the ladder to the wall. Then you have another normal force, a reactionary force up there. I think they're talking about just one. So if there was an answer that said 0, I would be like, that might actually be the answer as well. But it's either going to be 250 or it's going to be 0. And this is the force between the wall and the ladder. So then the next one is, and that's the only X forces we have. We only have these two X forces, the normal and the tension. How does the magnitude of the torque produced by the weight of the ladder, so we have a torque and weight, so that's the mass times gravity of the ladder and the ground contact, compared to with the torque produced by the weight of the ladder and the ladder wall contact. Okay, so this is a seemingly complicated question, which I've already answered, and it's not actually all that complicated. We know that the ladder is not spinning, so we know it doesn't start spinning. We know it never spins. We know that time can, go on forever, so that's not going to be 0, which implies that this alpha is 0. We have alpha up here, which we know then has to be 0. So the angular acceleration, how much faster it's spinning, is 0. Therefore, the torque, which is the moment of inertia, is basically an angular equivalent of mass times alpha equals 0, because alpha equals 0. So total torque, the net torque, the sum of all torques, equals 0. So as we talked about up here, we're basically going to have two sets of torques. One clockwise, one counterclockwise, one due to gravity, one due to tension. And since we know that it's not spinning, these torques have to equal, when you add them together, have to sum up to 0. And so from this point, we can say that torque ladder ground, which I'm going to say is right here, and torque ladder wall, which is right up here, since they have to equal each other, since they have to add up to 0, their magnitude have to be equal. So it's going to be C. That's a complicated way of saying a very simple idea. Long story short, ladder's not spinning, total torques all have to equal each other, therefore they equal each other and it's all zeroed out. Same thing as if you looked at it from a linear point of view, we can intuitively say that all the forces equal each other in the linear x and y side because the ladder isn't accelerating in one direction or another. It's not moving. So that's a complicated way of saying that the torques in this case have to equal each other. What is the mass of the ladder? Aha! So this is a little bit more complicated. This is some actual calculations at this point. Okay, so we can do this. So we want to look at our definition for torque. So torque equals R cross F. This is a cross product, so that'll means that, right this way, it implies that the magnitude of the torque will equal the magnitude of R times the magnitude of F times the sine of theta. So we'll look at the torques that we have here. So we'll look at this torque right here. So this will be, we'll draw a triangle here. Do I have that triangle the wrong way around? I think it actually is supposed to be this direction because it's stationary here and pulling that way. And this is stationary there, pulling that way. So that should be probably clockwise. And this one will be torque counterclockwise. There we go. I guess since I'm dealing with magnitude, it's not a big deal, but it's good to be correct. And it might matter here with which angle we use. So we have, I'm going to say R here because this is the radius, and this is our force gravity. So let's see that. How do we look at this? So the angle we actually want to use for theta is not this theta here, but this angle here. I'm going to call this phi because they already kind of used theta up there. One way you can look at this is you have your vector, force times gravity, going this way. I'm going to multiply by -1 just to move it up here. Then you have your r this way, and you have rf. And this theta would then be the same as that theta. Another way to look at it, which I think would be a little bit more intuitive, is, let's see here, trying to erase some of this without erasing too much. There we go. That seems reasonable. A little bit purple, put in back the R. The idea of a cross product is only things that are perpendicular matter. And it kind of makes sense when you see, an X. It's like, okay, everything there is perpendicular. It's only the perpendicular parts that count. So what you do then is you take this and you break up the triangle into, so you have R like this, and you break the triangle up into, and so R, this will be R y component, and this will be R x component. No, it's totally backwards. R x, R y. And then we have our force times gravity here. And so the only part of the x that's going to matter will be this portion here, the x component, because that's the part that's perpendicular to gravity. So torque, I'm going to call this torque ground. That's good. Torque ground will equal, this will be R, which will be L over 2, times the force, which will be mass times gravity. And that will be times cosine of theta. So cosine here gives us this side down here. So with this Rx, this radius that's perpendicular component, we have this portion times Fg, which is how we get the mg cosine of theta. And if you look over here, when I talked about, well, we want to use this angle over here, well, with that really, the way you'd find that angle is you do 180, which is the number of all angles of the triangle, which is the sum of all the angles, minus 90, because you have a right angle here, and then you have a subtract off the 29. Well, it's 180 minus 90 is just 90, so you have 90 minus 29. And the sine of theta in this case would equal, sine of theta is the same as cosine of 90 minus theta, which we found up here, where 29 is theta. So it makes sense then that we would then use the cosine for this, even though we're really looking at a sine, is because we're looking at another angle in the triangle. This is all just different ways of looking at it. Whichever way makes the most sense for you, go with that one. The one I would recommend is remembering that, because this is more intuitively correct, is that cross product is measuring how much something is perpendicular to another. So multiplied by the magnitudes. So for this radius r here, so we have r, I know, little r, big R, they should all be the same r's. You want to find the part that's perpendicular, which is this part right here. You could also kind of write this as, instead of rf sine theta, you could do r little perpendicular sine and then f. So it's the perpendicular component is what you're looking for. So long story short, we can write the torque with the ground like this. Okay, so now we want to look at the torque with respect to the building. Whoop. So looking at the torque of the building, green. So up here, we're going to have another triangle that looks kind of like this. So this is still going to be theta. This right here is going to be force tension, and then we're going to have R like this. So torque building, BLDG, that seems reasonable, will be, so we'll break this up into components. So this will be Ry, this will be Rx. Ry will be the portion that's perpendicular to the tension, so that will be sine theta. So this will be L over 2, which is R, times sine of theta, times force tension. Okay, and now we know that these magnitudes have to be equal. So I'm going to set these, and these are just magnitudes here because there's no arrows involved, there's no vectors. And so I'm going to set them equal to each other. We know they're going to be opposite directions. Oh, it gets that way and that way. I know, confusing. Whoop. Whoop. That's why I try and keep an intuitive understanding of these things. That way when my math goes way off the rails and my pictures get funny, I still kind of understand what should be going on. L over 2 sine of theta times force tension. Okay? So we'll start canceling out things. So masses don't cancel. L's will cancel because it's and that's just because it's at the middle of the ladder, which is convenient. Ooh, the 2's cancel as well. And we're looking for mass. That's our question mark. That's a terrible arrow. So simplifying everything, we'll have mass equals force tension times sine of theta over cosine of theta over a gravity. Sine theta, cosine theta, gravity. Does that seem reasonable? That does seem reasonable. Okay, so now to Wolfram, where theta is 25. So we'll do something like this. Oh, that's Wikipedia. Wolfram. And we have, need to remember what I was looking for. So this will be 250 over gravity, which is 9.8, times tangent of 29. Okay. 250 divided by 9.81 times tangent of 29. That's degrees. We get 14.13. 14.13 equals 14.13. This will be in kilograms. Look at our possible answers over here. We have 14. I'm going to call that the answer. Okay, to backtrack to kind of show what we did there, because the path I took for that was quite circuitous, treacherous, labyrinthian. So, what is the mass of the ladder? So if we look at this, our thought process is, okay, this ladder is not moving, therefore it's not accelerating, therefore the forces and also the torques, the net of each of those has to be 0. So we said net force equals 0, net torque equals 0. We drew our crazy diagram here. We had 4 different forces, but 2 of them were parallel, 2 of them were perpendicular. So we had force gravity down, we had force net up, and the reason we only had one force here is because the ladder was free to slide, which means there's no normal force in the x direction. The ladder was also free to slide up and down, so when the ladder was leaning against the building, there was no normal force in the y direction. So we had just one direction for the normal force. And then we had a force of tension due to a rope. And it kind of makes sense too, because without this rope, there's no way this ladder would slide down. It would be able to stay up there. It would always slide down. So we looked at our torques. We defined our torque as R cross F, which another way of thinking of that is the perpendicular component of the radius times force, which is written as RF sine theta, but I like this little perpendicular thing better. We then found our perpendiculars, multiplied it by the force. We then found one torque going one direction, one torque going the other direction, set the magnitudes equal, because they have to sum up to 0, and then solved for mass. Wasn't too bad. Okay, so now we're going to look at the last question. A person is now climbing the ladder. Compare the tension in the cable when the person is on the bottom step of the ladder, the tension in the cable, the person is on the top step of the ladder. Okay, so I'm going to draw a picture, kind of like this. Oh yeah, I think it's good. And this is going to be force, mass times gravity, force, tension. This will be force normal in the y direction, force normal in the x direction. Okay, so the reason I drew the mass times gravity down here is this is where he's on the first step. And so when we look at this, we're going to write this out. So I'm basically going to resolve the problem we just did. So we're going to look at the torque down here and the torque up there. So torque ground, I'm going to say this part here, is going to be R cross F, which we already solved, which will be, I'm going to say R small, because it's this R right there, R, because it's going to be a relatively small R because it's close to the bottom, times force gravity times cosine of theta. And we already determined why it's cosine earlier, because we're looking with Rx, which is the perpendicular component with respect to force times gravity. Okay, torque wall will equal, so the torque on the wall will be R, I think this is normal R because it stays the same, times force tension times sine of theta. Okay? In solving for force tension, we're going to have, set these equal to each other. Let's see if I can do this in my head. Can I do this in my head? I don't know. Wait a second. Yes. So this would be R small times force times gravity times cosine of theta all over normal L. I'm going to call this L over 2. L over 2 times force, nope, not force tension because that's the thing I'm solving for, times sine of theta. Okay? Now when we look at this same issue, but like this, so we have our ladder like that, and now we have same force tension. We have mass gravity up here because he's on the top step. We have force normal in the x direction, and we have force normal in the y direction. We get a similar thing. T ground, or torque ground, will be R big, because now we have a much bigger radius, bigger x component, times force gravity times cosine of theta, because we have the same theta. Torque wall will then be L over 2, it's supposed to be an L, times force tension times sine theta. Solving, setting these equal, and solving for force tension, we get, I'm going to call this force tension top step. This will be force tension bottom step, will equal R big force times gravity, or force due to gravity, there we go, times cosine of theta all over L over 2 times sine of theta. And we want to compare force bottom to force on the top. Put this guy right there, move it in, that's about right. And so, get a good contrast color. We want to see which one of these is bigger, the force tension when it's on the bottom or the force tension when it's on the top. Cancel, 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 cancel. Shouldn't be a dot there, that's okay. Cancel, cancel. And we're left with R small is less than R big. So this side, this will be a bigger sign here. Left with this, we'll look at this one, look at that one, and we have force tension on the bottom will be less than force tension on the top. And, let's see if that's a possible answer. Force tension on the bottom is less than force tension on the top. Okay, so it'll be this one right here. So there's the overly mathematical, analytical way that I did it, where we set up two scenarios. This is when it's on the bottom, this is what's on the top. I solve for tension on the bottom, I solve for tension on the top step, and then I start canceling everything out and then see which one is bigger. Solve the inequality. Now, granted, this is the timed evolution, and this is one of the earlier problems in the test, so you're not going to have time to go through this. You're going to have to kind of look at this and be like, okay, this is what's going on. So for this question, I would recommend drawing out the picture, because what happens here is you have this picture and you have this picture, and your immediate thing you notice here is the Rx component there is small, the Rx component here is big. And so you're like, all right, it kind of seems to sort of make sense then that with this small, we're multiplying by a small x component here, the small x component of the radius, that's going to then give us a smaller overall tension. And you might kind of be able to reason it out too, like, all right, if I was on a ladder, how taut would this rope be against the wall? So that is kind of the intuitive winging it method, which honestly, for this kind of problem, you're probably going to have to do. And then also the more analytical, mathematical way of going through it, which that's a lot of writing for not a lot of points. So hope that helped. I will see you on the next problem.